Welcome back to lesson 6 of our examination of the transport layer of the TCP/IP model based on the text by Jim Couros and Keith Ross, Computer Networking, a Top-Down Approach. You'll recall in the last lesson we were introduced to RDT 1.0, which was a representation by the authors of a network that would have no errors, no speed limitations, no problems at all with routers along the way losing bits. And it was a very interesting model showing a couple of different states of the application, requesting the transport layer package the data and send it on to the destination, the transport layer then passing the data down to the next layer, to that unreliable network, and then the data being received at the other end in the form of a TCP segment and being passed up to the application layer of the end system. That's a pretty nice fantasy, but in the real world it really doesn't exist. And then toward the end of that last lesson, we were introduced to RDT 2.0, which introduced a new problem. And that problem is that bits might get lost in transmission. And therefore, the receiving unit has to be able to recognize that there is an error in the segment that has arrived. And RDT 2.0 that we're about to talk about shows us how that problem is solved. We did have a little introduction to RD 2.0 with some suggestions on how that happened. And that happened by means of acknowledgments and negative acknowledgments from the receiving unit to the sending unit, and the use of a checksum to validate the data. What we found out was that in this RDT2, the transport layer ran a hashing program to create a checksum number that was included in its segment header. And when the segment arrived at the other end, the receiving transport layer would run that same hashing algorithm on the bits that it received, and if the number found in the header, in the checksum field of the header, was the same, then that indicated that the bits arrived intact and in one piece, and it would then send an acknowledgement back to the sending unit, letting it know that they had received the data successfully. If, on the other hand, after running the checksum hashing algorithm, the numbers did not match, then it would respond to the sending unit that the data was not correct, expecting a retransmission. Now in this lesson we're going to find out how that takes place using these states. Now in RDT 2.0 we're going to see how the problem is solved using the acknowledgments and negative acknowledgments by means of the finite state machines. In this figure here, we see the state representation of RDT 2.0. Remember, this is a data transfer protocol employing error detection, which includes positive acknowledgments and negative acknowledgments. The initial state of the state machine is indicated by the dashed arrow there. Wait for a call from above. Remember, RDT 1.0 only had one state in the sending side and one state in the receiving side, but RDT 2.0 has two states on the sending side. First state is waiting for a call from above, and the second state is waiting for an acknowledgement or a negative acknowledgement. The send side of RDT 2.0 has two states. In the leftmost state, the send side protocol is waiting for data to be passed down from the upper layer. You'll notice the little symbol below the horizontal line down there under RDT_RCV. That indicates no action, which is the initial state of the state machine. When the RDT send data event occurs, the sender will create a send packet containing the data to be sent along with a packet checksum, and then send the packet via UDT send packet operation. In the rightmost state, the sender protocol is waiting for an ACK or an ACK packet from the receiver. If an ACK packet is received, the notation RDT receive packet ampersand is ACK receive packet corresponds to this event. The sender knows that the most recently transmitted packet has been received correctly, and then the protocol returns to the state of waiting for data from the upper layer. If an ACK is received, the protocol retransmits the last packet and waits for an ACK or an ACK again to be returned by the receiver in response to the retransmitted packet. It is important to note that when the receiver is in the wait for an ACK or an ACK state, it cannot get more data from the upper layer. That is, RDT send event cannot occur. This will happen only after the sender receives the ACK and leaves this state. Therefore, the sender will not send a new piece of data until it is sure that the receiver has correctly received the current packet. Because of this behavior, protocols such as RDT 2.0 are known as stop and wait protocols. That's a term you need to know, stop and wait protocols. It sends a packet and then waits for an acknowledgement. The receiver side of the state machine for RDT 2.0 still has a single state. On packet arrival, the receiver replies with either the ACK or a NACK, depending upon whether or not the received packet is corrupted. The notation RDT underscore RCV receive packet ampersand corrupt corresponds to the event in which a packet is received and is found to be in error. Okay, let's take a look at some of these steps as they occur. As we can see from this image on the screen, both the sending and receiving sides are waiting for a call. The sending side is waiting for a call from above, from the application layer, and the receiving side is waiting for a call from the below, which would be the next level down layer, the network layer. The application has sent a message down to the transport layer, where the transport layer has created a segment in which it's bundled the appropriate information, including the checksum, and then it goes about sending that message down to the unreliable network below, where it traverses the network and arrives at the receiving side. And now the receiving side has received a message from the below. In this case, it's identified the message as not corrupt, and therefore it retransmits an acknowledgement back to the other side, which then resets to waiting for a call from above. Now here's an error situation. The sending side is waiting for a call from above in the application layer, while the receiving side is waiting for a call from below from the lower level network. The application transmits the message down to the transport layer, where the transport layer bundles the message into a segment, including the checksum and so forth. And then the transport layer then puts that message out on the unreliable network below. It's received at the receiver side, which was waiting for a message from below. But this message has been viewed to be corrupt. And therefore, this time, it sends a non-acknowledgement, a negative acknowledgement, back to the sending side, where it is received, and the sending side will retransmit the packet again to the receiver, where it is approved this time. It's been recognized as being valid, and it sends an acknowledgement back to the sender. Now, what's the problem with that? Protocol 2.0 may look as if it works, but unfortunately it has a serious flaw. In particular, we haven't accounted for the possibility that the acknowledgement or the negative acknowledgement could be corrupted itself. At least we will need to add a checksum bits to the acknowledgement and negative acknowledgement packets in order to detect errors. The more difficult question is how the protocol should recover from the errors in the acknowledgement or negative acknowledgement packets. The difficulty here is that if an acknowledgement or a negative acknowledgement is corrupted, the sender has no way of knowing whether or not the receiver has correctly received the last piece of transmitted data. Consider three possibilities for handling corrupted ACKs and NACKs. For the first possibility, consider what a human might do in the message dictation scenario. If the speaker didn't understand the OK or the please repeat that reply from the receiver, the speaker would probably say, "What did you say?" Therefore introducing a new type of sender-receiver packet to our protocol. The receiver would then reply, "But what if the speaker's 'what did you say' is corrupted?" The receiver, having no idea whether the garbled sentence was part of the dictation or a request to repeat the last reply, would probably respond with, "What did you say?" And then, of course, that response might be garbled. The second alternative is to add enough checksum bits to allow the sender not only to detect but also to recover from bit errors. This solves the immediate problem for a channel that can corrupt packets but not lose them. A third approach is for the sender simply to resend the current packet of data when it receives a garbled ACK or NACK packet. This approach, however, introduces duplicate packets into the sender to receiver channel. The problem with duplicate packets is that the receiver doesn't know whether the ACK or NACK in the last sent was received correctly at the sender. It cannot know whether an arriving packet contains new data or is a retransmission. A simple solution to this new problem, and one adopted in almost all existing data transfer protocols, including TCP, is to add a new field to the data packet and have the sender number its data packets by putting a sequence number into this field. The receiver then need only check this sequence number to determine whether or not the received packet is a retransmission. For this simple case of a stop and wait protocol, a 1-bit sequence number will suffice, since it will allow the receiver to know whether the sender is resending the previously transmitted packet or not. If it's a new packet, then the sequence number will be different. If it's retransmitting the old packet, then there will be the same sequence number. Since we are currently assuming that a channel does not lose packets, ACK and NACK packets do not themselves need to indicate the sequence number of the packet they are acknowledging. The sender knows a received ACK or NACK, whether it's garbled or not, was generated in response to its most recently transmitted data. With stop and wait, the sender sends one packet and then waits for the receiver response. At some point in these iterations of the RDT model, we're going to recognize that with this stop and wait protocol, a great deal of time is spent waiting with nothing taking place. I think we can count on seeing that one solved at some point soon. Before we move into the state machines of the RDT 2.0 model or the RDT 2.1, whatever it's going to turn out to be, why don't we take a break? This has been a really information-filled session. Spend some time, go over your notes, maybe even rewatch part of it. So I'm sure there's things that we missed. And take care of any business that you might have. And come on back and we will go after lesson number 7.